Hello, and welcome to my presentation. I'm Wählby, and I will present Tissue Maps. So Tissue Maps is a browser-based tool that we developed to make it possible to share and explore large spatial omics data via a web platform. The 3.0 version that we present today can show tens of millions of data points on top of multi-resolution image data, thanks to GPU acceleration. So analysis of tissue morphology via standard H&E staining is powerful, but provides limited information on molecular heterogeneity and potential drug targets. At the same time, bulk analysis of tissue gene expression provides limited information on cell organization and spatial interactions. And recent methods, such as in situ sequencing and spatial transcriptomics, combine tissue morphology with spatially resolved gene expression and has a lot of power. The resulting data is very rich. Hundreds of different genes can be detected in parallel. It's also high in resolution, meaning that we can detect the gene expression at subcellular resolution. Furthermore, it's comparably high in throughput, meaning that we can analyze several large tissue samples in a single experiment. The data also calls for two different types of investigation. First, unspecific high-level investigation means that we visually interpret the information. We look for patterns, construct hypotheses based on prior knowledge. Next, we also want to do investigation by low-level hypothesis testing, meaning that we seek representations of the data where we can test our hypothesis by some kind of quantitative description of the data. A simple example would be that you may want to quantify the expression of several genes at different distances to the edge of an aggressive tumor. In both cases, interactive visualization at multiple resolutions and exploration by experts in both pathology and image analysis was needed. So the challenge that we wanted to address is viewing and sharing our large spatial omics datasets without having to download large files or install any software, very much like viewing data on Google Maps. We also wanted to make it possible to interact with the data, see the results of spatial statistics, define regions of interest, play with clustering alternatives, and check decoding quality. All this should be done at a range of different resolutions. There's, however, a key difference between this visualization and Google Maps, and that is the fact that we cannot subsample the information as is done in Google Maps, since all information on the probes and targets we're looking for is relevant also at the lower resolution. I will show you a quick demo of what the resulting web interface looks like. Here you can see a series of sections through the developing human heart, and if we zoom in, we see cell nuclei as gray blobs, and then we can turn on and off the visualization of the different markers. In this case, representing more than 100 different genes expressed during embryo development. We can also choose to only show a few specific genes and look at them across the different samples. If we want to, we can also zoom in and draw regions and extract information on expressed genes within such a region. And once the region has been drawn, both the gene list and the regions can be saved and shared with others, for example, in a collaborative project. And we can export all the both the regions and the information extracted from a given region. We can also load data that has been pre-processed in some way. In this case, rather than showing the individual genes, we have used a neural network and color-coded neighboring genes based on their local neighborhood composition as a representation of the different cell types in the tissue. And you're more than welcome to explore this data set that is openly available on the web via the Tissue Maps website. It's also possible to interact with other representations of the same data at the same time as you see it in the tissue sample. Here we wanted to explore niches of similar gene expression in the tissue. And based on the region of interest, we created a UMAP embedding on genes with similar neighborhoods. We can then manually select regions in the UMAP space and see where the corresponding markers are located in tissue space. We can also go back and select such a region in the tissue space and directly extract localized gene expression statistics. Another alternative is to do fully automated clustering by k-means clustering here and see the result of different regions in the tissue. This is done via a plugin connected to Tissue Maps. And you can then also, if you want to, go in and interact with the different parameters for the cluster setting and also extract information per each of the regions. After seeing all these markers, you may start to wonder where they come from. In this case, they come from in situ spatial transcriptomics. This is a collection of different techniques for mapping gene expression directly in tissue. And all these methods are conceptually very similar. It's usually large image series and combinatorial labeling of the expressed genes. And decoding is challenging, both due to low signal to noise ratios, background fluorescence, dense signals, and jitter or movement of the signals. So there are a number of different methods that have been developed to decode this type of data. And the tricky thing is then the evaluation of these different decoding methods, mainly because of these large image series and information at multiple scales. And there's very often difficult to have a really good ground truth. So this is where tissue maps can be really useful to explore the quality at multiple resolutions. So tissue maps allows you to load these gigapixel images and then see these gene labels on top of the data and then use this QC tool, which I'm showing here. So once you have loaded all the data from your experiment, you can click on a marker, and that is the output of your decoding scheme. And then once you click on one of these markers, you directly see the associated raw data and the decoding path so that you can easily confirm or discard the result. So you see, you click on a gene and then you can just follow it through all the different image channels and cycles of decoding. And you can also see what gene it is and visually then relate it to the tissue morphology to confirm that what you see is true signals and not artifacts. So tissue maps allows for 3 types of input data. First of all, 2D images, where we limit to display 8-bit data, which means that 16-bit data would need to be rescaled. We use bioformats for loading, and we can work with any modality or combination of modalities and multiple layers. It's also possible to add regions drawn manually or regions automatically defined by tools such as QuPath and Cellpose, or generated using one of the tissue maps plugins that I just showed. And the regions that are saved should be in the GeoJSON format. We can also load markers, which is simply a file with X and Y coordinates, type and value. And it could also contain more advanced information, such as information to build pie charts. And here we use the simple CSV format, which can also be generated from data. And the same format is used for representations also in feature space. So X and Y coordinates in UMAP space in the CSV file is what you need to do the interaction between UMAP and the tissue space. To conclude, Tissue Maps is primarily a web-based interactive viewer for large-scale 2D images, regions, and markers. We collaborate with other open source initiatives for cell and tissue segmentation and spatial statistics. and aim for compatibility rather than building all functionality into tissue maps. So please reach out to us if you have ideas or how your tools can be combined with tissue maps. And currently, we have examples of how tissue maps can be combined into or put into Jupyter notebooks to create like modular workflows. And we also have examples of how it can work together with Python, NumPy, TensorFlow, PyTorch, Cell Profiler, Napari, Fiji, QuPath, squidpy, ScanPy, and Giotto on our website. And with that, I'd like to thank you for listening and also thank the Tissue Maps team, as well as our funders, former team members, and collaborators for contributing to this exciting work with Tissue Maps. And if you want to learn more, please contact us or join our pre-recorded workshop. Thank you.